Okay, we start up again. So continuing with the convection diffusion equation that we had. Well, we can write it like this: rho u phi derivative, and then we had viscosity phi double derivative, something like that. And now we are going to go through some classical schemes first. How to discreticize this one. Instead of using the standard index notation with I and j here, we are going to use the classical Tatanka notation then with center point P and the neighbor points and so on. So here you have the center point, west point, east point, something like that. And the problem is your control volume will then be located somewhere here. And we need the phase values. We need the eastern values and we need the western values, small letters, on the cell faces. We need the fluxes. So how to evaluate that one? That is sort of the question. So what we have looked at so far, central. Then we are going to find a value phi on the eastern face. We just take the average between these two. Linear interpolation. Straightforward. So that one will now just be the center point, and then the eastern point, and then divided by 2. If you have the location in the center between these 2 points, or else you have to use some delta x1, delta x2, and so on. But linear interpolation. And then the same for the western point. I don't even bother writing that one up. For the first order upwind. First order upwind. What do we do then? Then we do it very, very crudely. Here we now say the transport velocity here, u is positive, information goes to the right. This one is simply equal the center point. We do it as crude as that. That is the first order upwind for you. Terrible, awful. But it works, and it's very, very stable and nice and whatever. Then we start doing things a little bit more advanced. And how to do that? Well, then we have to address more points to increase the order and looking again upwind. The central schemes, if you sort of increase this one, going both west-west and even east-east, it's possible, but it doesn't become more stable. It doesn't help. So a central scheme here, we have to go upwind, I'm sorry. So a little bit more advanced, linear upwind. Upwind. This is actually second order accurate. So here we do it a little bit more advanced. So this one will now read the center point, and then we will have plus, and then I'll have the difference here between the center point and the western point divided by 2. Something like that. So you see the center point has a weight 3/2, and then minus the western point 1/2. Linear upwind. So you are using, say, these 2 points to create one value here. Instead of this one, you just use the center point alone. And yeah, we could have continued here. People have tried many things. And it was only until they started looking into what's called the total variation that they have any degree of success. To get that, let's write this one on a different form. I don't want it like this. Well, we can write it here actually. I want as a generalized form. Generalized form. I want this eastern point to be written as first the center point, and then I want a function psi. I want a function multiplied with 1/2, and then the difference here with the phi east minus the center point, phi p. Did I do something wrong there? Let's see. No, it should be right, I think. Yeah. Okay. I want everything on this form. And then we have to find this function. Well, for the central, then what will he be? He will actually then be just 1. This function here is just 1. Okay. Very easy. For the first order upwind, well, then he has to be 0. Very easy. For the linear upwind, then he becomes a little bit more tricky. How will he then look? Well, you have to rewrite it a little bit to get it on this form, and it's going to look something like this. Let's see now. Oh, I need more space. Let's do it like this. So you will have something like this. You will have phi p minus phi west divided by phi east minus phi p multiplied with 1/2, and then you have this one phi e minus phi p, something like that. Then this one will fall, and we are back to what we had. So that's the linear upwind, linear second order upwind. And this one, this ratio here, that one we are going to baptize as the argument for this function. This one I will call the argument, small r. This actually is then for the eastern phase alone. And what is this actually? Let's see now. At the top we have the difference between these two. Okay? And at the bottom I have the difference between these two. So this argument, this r argument, is actually the upwind divided by the central. Sort of a ratio there. If you can see it, the difference here divided by the difference there. That means for this linear upwind thing, he will then be my function equals, when I want it on this generic form, well, I have this one already, then he's just r. Done. So these are the 3 that we have so far for this function, whatever that function is. Now we can start playing around with schemes. So remember this one? Any questions so far? That's okay. Good. Then removing this one. So then we have to talk about variation, total variation. And what we are seeking is actually a reduction or a removal of what we call total variation. As you saw from the test simulation there, we had for the central scheme, when he explodes, you get an undershoot, and sometimes you can also have an overshoot, and you don't want that. So we want to get rid of these, say, results. So let's have a look at total variation. Total variation for a function, sometimes called just TV, of any function phi, is actually just the sum of all the difference, phi1 minus phi2, absolute value, and then plus absolute value of phi2 minus phi3, plus absolute value, and yada yada yada. Just continue. You just add all the differences, but with an absolute value. So if you have something like this, here you have a phi, and then you have a phi looking something like that. What will the total variation be here? Here you have many, many points. Well, if this one is 0 and this one is 1, then the total variation here is going to be 1. Somewhere you will have a difference from 0 to 1, depending on how these points are spread out. But here you don't have any variation at all, nor here. So there, the total variation is 1. So that's good. Fair enough. And what we really want is a total variation diminishing. Diminishing. I want to have the following property. My total variation of any variable, say at iteration or time step or whatever, level n plus 1, should be smaller or equal to the previous one. Then I am sure that my solution is going to be bounded. So if I have a sort of a sharp jump here at one iteration or one time step or whatever, then the next one, he should not start doing something like this. Then he will violate this one. He has to be equal or smaller. No way that he should do something like that. So this is to get rid of under and overshoot. We want to bound him, limit him. That is the idea. Okay, how to achieve that one? Well, we have a guy called Sweeby in '84. Sweeby, he said, yes, this is going to be TVD if. And then we have some criteria. And the criteria goes for this strange invented function psi. If that one, if he is smaller than the smallest of 2r and 2. Let's see now, we're going to need a diagram. Over here, here I have my psi. Here we have 0, here I have 1, here I have 2. My argument, that was this ratio between the upwind versus the central scheme, the small r. He should then say have 1, 2, yada yada yada, something like that. So what are we talking now? We should be below the line number 2, Okay, and also the 2R line. What's this? Let's see. Here we have that is just R. Psi equals R. Psi equals 2R must then be something like this. And we have 2R. Something like that. Or did I choose? No, I said it the wrong way, didn't I? It must be here. Thank you. Here we have 2R. It's much steeper. So this is rubbish. Okay. So the first criteria, stay below 2 and stay below 2R. Okay. You have to be down there. Fair enough. But we have more. And well, for our scheme so far, the upwind scheme, well, he was just the x-axis here, so he is down. That's okay. The central scheme, that was 1. He is okay unless you reach this area. So R has to be smaller than 1/2. Bigger than 1/2. Then you should be safe. And then we had this linear upwind. Well, he was this line here. He should be okay unless you go too far. Then he goes above 2. Okay. We have more demands. We want second order accuracy. Demand second order. To achieve second order, it turns out that your function R, and you use the argument equal 1, then the function has to be 1, meaning you have to go through this point. You have to pass that point precisely. 1, 1. And that's okay for our linear upwind scheme. Psi was equal R. Is okay for our central scheme. I mean, he was constantly equals 1. But of course, the first order upwind, he fails. He's all the way down here. So now we got rid of that one. That's good. And then also we needed to be bounded. That's the third demand. Should be bounded. Actually then by our linear upwind differencing scheme and our central differencing scheme. Okay, so the linear upwind, that was this one and it was this one. Hence, we have to stay inside here and then inside here as well. So there you see we have some limitations where you should be for this function psi to keep it as a TVD scheme. You have to be inside here. And now, well actually it's sharper than that one. Yeah, you can't have it here. No, sorry, that was wrong. We have to be below that one now. We have to stay here and then here. Yeah, that's more correct, isn't it? Yes, we have the line R and we have that one. Yep. And that's the limitations that we are needing to achieve a total variation diminishing scheme. And then comes the genius. You can invent any function, whatever you want, as long as you are inside this region. So you can create a function looking something like this, for instance. As long as you pass this point and you stay in these regions, then it's okay. So this is a TVD scheme, actually. Total variation diminishing. Actually, this UDS scheme that we had down here, C was equal to 0. This was also a total variation diminishing scheme, but it was only first order, so he misses the second order criteria. But he will be, say, a TVD scheme actually. So for such a problem like this, he's going to smear out this gradient quite sharply. So yes, you will have smaller and smaller total variation there. Or actually in there it should be the same. But never mind that one. So this is what we want. And this is what we get. Any questions to that one? Let's have a look. So this one is taken from the textbook by Versteeg, and here you can see a whole bunch of these different modern schemes. And yes, you have to be in this range here and in this range here. And he has drawn in some different suggestions. And which one should you use? Nobody can tell. Depends on the problem. So here you are talking trial and error. You can't really say that, that one should be best for this problem. You can't say that in advance. You have to try them. But I mean, it's quite obvious to be dead certain. Choose one of these, say, that will be inside this range no matter what. And as you can see, you have a whole bunch of them. Maybe one is better than the other, but that will be problem dependent. You can't tell that in advance. You have to try them. And yes, all of these and more is available in OpenFOAM. So we have them as options. So let me just show you here. It's a nasty problem. You have given the velocity field, constant velocity, 45-degree angle. And then you are sending in a quantity here called t. You have 0 on the left and the bottom. But in a range here in the corner, you put that one to be equal 1. And then you say, for this problem here, it's a steady state problem, or you can have time if you like, but I don't have any viscosity. I don't have any diffusion mechanisms. That means this change from 0 to 1 here should stay dead sharp. So this is then the analytical solution. If you draw a line, either like that or like that, you will have a sharp jump in the unknown t. So whatever quantity you have. Simulating that one without viscosity, well, that's the Euler equation actually. That's not so easy. And the solution here for this exercise looks something like this. So here we are tried with several schemes. We have second order central. Well, now we know that one is terrible when you don't have viscosity. And yes, he's unconditionally unstable. And these over and undershoots, they will just be bigger and bigger as time goes by until he explodes. Not good. Then we had the first order upwind, the green one. You see he really smears out everything. He adds way too much viscosity into the problem, but he's dead stable. But at a terrible price, because the exact solution should be a square. For the linear upwind, second order accurate, well, here was a TVD scheme within limits. And as you can see here, actually the red line, you get under and overshoots. So that was not the point. We shouldn't have it, but we got it here anyway. So he's not a TVD scheme. And then a couple of the more advanced. One called Super B and the other one called Van Leer. And they use, you can see yourself, they get it quite nicely actually. especially for this case, the Super B very, very close to a straight square. Although, I mean, this problem is purely academic and impossible to do in real life. You will always have viscosity in a real problem. So it's a little academic, but at least there you see the effect of these schemes. Let's see, where were we? Yeah, here also you see the same diagram where you should be, and the Super B here is sort of taking the upper part as a constant, a little bit messy to program, but it's possible. The Van Leer, much smoother and nicer solution. And where do you want to put these schemes in? Where do you want to use them? Well, then we have to go somewhere, say, where should we look? Cavity case, for instance. Yeah, the classical cavity case. And then we had, what was it? Gedit systems. And there we had the FV schemes. So this was a setup for our, I think the very first tutorial we went through. The cavity case, laminar but transient. So we haven't talked about the grad schemes yet. But the div schemes, as we call it here, there you see you have the divergence of then two unknowns. There you have the nonlinear term. And this is by far the most important one of all of these different schemes. So here you can now start playing around with different schemes. And if you do something like this, do the banana trick, and try to simulate. Let's see, where are we? Icofoam it was, I think. Then fatal, unknown conversion type, It has to be either Gauss or bounded. Bounded, what does that mean? Bounded, then you sort of force him to get rid of under and overshoots. You try at least to force him. So yeah, you could have used that second order linear upwind and included the word bounded. But most of them, they will have the word Gauss in front of them. So let's do that. Gauss, and then the banana. There you see your options. How many do we have here? Well, I only have 63 different schemes. Be my guest. So, meaning when you have a CFD task at hand and you have to choose a numerical scheme, then you simply do 63 different simulations and see which one was the best. Be my guest. Of course, you don't have to. I mean, many of these will be a little bit weird. You don't really know what they are even. You have to look it up, I guess. So, but some of them are, say, more and more famous. Super B, now you heard, and we had this.
It was raining before. I think now.
Yeah, but I mean, he has power, so why do you? Maybe he thinks I'm too boring. So. Okay, so sorry about that, you camera people looking. Well, anyhow, I'm not going to go into all this in detail. Just warning you, we can't really tell which one is best. So try a couple of them, it might be a good idea. But never ever end a report using this one. That's illegal. You can play with it to get things started, okay, but nothing more. Nothing more. You should definitely use a second order, and most of them are going to be. But don't just gamble on this one. You should sort of find what you are doing. Then yes, this is a TVD scheme and it's advanced and it's checked and it's okay. So just don't pick any of these. Old Quick, for instance, it's not a TVD. Don't use it. Well, part of it is, but no, not good. Yeah, you have a whole bunch of these. Okay, that was the topic for today. Yeah.
Is it a lot more expensive to run a simulation using one layer as a divergence scheme?
No, it doesn't cost you more. So it's definitely worth doing. But I would say, for most cases, if you can get the second order central scheme to run, that's actually the best one, the most exact, the most precise. So that would be the best. But he is dangerously unstable. But if you can make it work, beautiful. Which we could here in this laminar cavity case. So just a linear and then nothing more. That would be beautiful. But if it crashed, okay, then we have to stabilize it with the more advanced. Yeah. Other questions?